So this is our second talk on X-ray physics. This is a short one, mainly dealing with X-ray interaction with matter. So when I say X-ray interaction with matter, I'm mainly talking about X-ray interaction with people. That's the thing that we're shooting X-rays into most of the time. And there are three main types of, there are a whole bunch of different types of interactions, but there are only three that we care about from a clinical standpoint, and those are coherent scatter, Compton scatter, and the photoelectric effect. So let's go into detail and talk about each one of those. So we'll start with coherent scatter. This is a type of scatter or interaction that's going to result in a little bit of scatter that occurs in low energy situations, low enough that it's not a high enough energy to liberate an electron. And if you remember from the prior lecture, that's called ionization. So there's no ionization that occurs. Instead, you basically have an X-ray that does a flyby, and as it flies by, it loses some energy and it gets its direction modified just a little bit, so something like that. So it starts out coming in one direction and sort of comes out another one. So what does that actually mean? What is that? Who cares? So here are the testable points. It occurs at low energy, and it results in no ionization because it doesn't have energy that's high enough to do that. It's really only seen clinically in situations where low energy is used, and as I'll talk about in a future lecture, that is mammography, which uses some lower energies. It's not adding any additional dose because you're not creating anything additional to the X-ray that's already been pushed in, and it can result in some loss of image contrast because you're sort of messing with the normal interaction there. It is a form of scatter. Now let's talk about the bad guy, Compton scatter. So he's straight out of Compton. He's a bad guy, as the corporate media would have you believe, of NWA. That's how I like to think about this guy. So basically, you have an X-ray that is they're occurring at a higher energy relative to the coherent scatter, and it's going to strike one of these outer shell electrons, and as a result, it's going to knock that electron loose. It's going to fly away. You're going to be stuck with now an ionized atom, right? Because it's lost an electron, so now its charge is no longer balanced, and there's going to be redirecting of the X-ray. Now, this occurs in sort of a variety of flavors. In other words, it's not all or none. It depends on how the X-ray strikes the electron. If it's a direct hit, it's going to transfer more energy. If it's more of a glancing blow, it's going to transfer less energy. So it's variable on a scale. So let's talk about the things that are produced. So the first thing that's produced is a free electron. That's the thing that got knocked loose. The next thing is now you have an ionized atom, right? So it's missing an electron. You've also produced a photon. It was there to start with. This is your X-ray, but now it has a little bit less energy in a new direction. So you produced a new direction and slightly less energy. And as I mentioned, this is variable energy transfer. And because that's a difference from the photoelectric effect, that makes it a testable fact. So I'm sort of repeating it over and over and over again because I believe that repetition helps with memory. So another important fact regarding Compton scatter is that it does not care about the Z. That doesn't matter to it. Because it's dealing with the outer shell electron, it's less important. Now, what it does care about is how densely packed the atoms are. So, in other words, the density of the material. So, in other words, if you've got more outer shell electrons to crash into, or they're more tightly packed, it's easier to strike into. That can affect. But the big thing to remember is that the Z does not matter with Compton scatter. All right. Another issue is that Compton scatter is high energy. It occurs above 25 to 30 keV, whereas photoelectric effect and the coherent scatter occur at lower energies, right? So NWA is high energy situation, right? So they occur in high energy situations above 30 keV. They're the bad guy, right? Alright, so photoelectric effect is the good guy. Sort of sounds like a scientist-y name, or you can sort of remember that the other one is the other one. So photoelectric effect sounds more fancy. That's the good guy. Now, what is the photoelectric effect and how is it different? Well, photoelectric effect, instead of the X-ray hitting the outer shell like it does in Compton, it's hitting the inner shell. It's penetrating all the way to the core, and it's knocking off one of these inner shell electrons. So, and as you may remember from prior lectures, when you lose an inner shell electron, that's the good real estate, right? So one of the higher shell electrons is going to jump on that real estate. Oh, that's a good compartment, I want to move there. And then that energy difference causes a characteristic X-ray. So that kind of... So the energy released is going to be equal to the difference in binding distances between the two shells. So it sort of depends on which one drops down. But for tungsten anyway, you're dealing with 69.5 and 59, depending on if it's an M decay or an L decay drop. And these are by far the two most common X-ray productions. Another thing to remember is that you can't have a photon released or created that has more energy than the incident electron had coming in. So you can't put more energy out than you had, put in, which makes sense, but that's something that's sometimes testable. So the other thing that can happen, you may remember, is that you can produce this thing called an Auger electron. You may remember that that's a little different, where you still have a loss from an inner shell electron. You still get a higher level to move down, but this time, instead of generating a characteristic X-ray, it gives off its energy in heat, and that heat is then transferred to an outer shell electron, which then causes it to sort of take off. So you actually bumped two of them out. And this occurs more at tissues that are made up in the body, right? Because you're not hitting tungsten, you're hitting flesh, you're hitting carbon, right? So that's a lower atomic number. So you're more likely to end up in this range here when you're dealing with physiology. So that's actually more likely to dominate. But the photoelectric effect is still a good thing. It's much better than Compton for a couple of reasons. It contributes to contrast, whereas Compton just makes noise, right? So you can think of NWA, they're just making noise. And a photoelectric effect, I should back up. For you foreign medical grads, NWA was a band in the 80s in America that was based out of Compton. Dr. Dre, straight out of Compton. If you haven't heard of him, you want to YouTube it, because it's some of the best music ever made. So, moving back here again, photoelectric effect, it's good because it's contributing to image contrast. Compton just makes noise, and this is all or nothing. I remember that I said with Compton that there was variable image transfer depending on if it hit sort of sideways or if it hit directly. The photoelectric effect is all or nothing. So, and that's the way that I like to practice my life, so that's the way I remember that that's the good guy. The good guy goes all or nothing. He doesn't do anything halfway. He's going all in, or he's not going at all. And also being the opposite is that the probability of the photoelectric effect is directly proportional to the atomic number cubed. So this does matter, okay? And as we mentioned before, photoelectric effect dominates at low energies, whereas Compton is a more high energy thing, and that's so it's the opposite. So let's compare and contrast here. Compton is bad. It's like a drive-by, which also happens in Compton. It just makes scatter, and this drive-by, of course, is also hitting that outer shell electron. Photoelectric effect contributes to the image. Compton's a high energy place, dominates at the higher energies versus the lower energies. It doesn't care about the Z, right? It's not following the rules, doesn't care about the Z. And the photoelectric effect, as our nerdy scientist guy, he does care about the Z. The drive-by is hitting the outer shell, and the photoelectric effect is going all the way in to the core, and it's that all or nothing effect. So photoelectric effect is more desirable, and it's more desirable because it discriminates not only on the basis of tissue not only on the basis of atomic number, but also on tissue density, because you're getting those, you could be getting different characteristic X-ray production and like this. So it behaves differently depending on the atomic number and on the density. Remember I said that the Z matters? So both of those matter. So whereas Compton scatter only discriminates based on the density, like blocking or not blocking, that kind of stuff, doesn't care about the atomic number. And also, it causes scatter, which does two things. One, it reduces the contrast, and two, it constitutes a radiation hazard to the staff. So you're generating scatter within this patient, which is flying back at the X-ray tech or whoever's unfortunate enough to be in the room with the patient. Okay, so let's move on to another topic that's related. This is a graph that's showing attenuation and photon energy. So at low photon energies, you having a lot of the X-rays are getting attenuated because they've got low energy. They don't have enough energy to sort of push through. And at high photon energies, you're getting less and less attenuation because they're just zipping right through like a bullet. But then you notice that there's this spike, that thing, and that's called the K-edge. Basically, this is the sweet spot where you've got photon energy equaling the binding energy, and this causes a abrupt, sharp increase in the photoelectric effect at this sweet spot, and it gives you maximum contrast. So this is a good thing. So what is contrast? Well, contrast means you can see a white thing next to a black thing, like distinguishing two things that are next to each other based on their color, essentially, is contrast. So black, white, black, white. It's very easy to see there's a white thing next to a black thing, right? But if I had a black thing next to a thing that was like a dark gray color, then it may be more difficult to see those things next to each other. So you want to set the KVP twice the binding energy of the contrast agent being used. And you may remember that when X-rays are filtered normally, this isn't like in a diagnostic setting, that the average energy is going to be between 1/2 and 1/3. I mentioned that in the prior lecture. That's why you want to do twice here. So the iodine K-edge is around 33, and so you want to have your KVP set to at least 66, and then barium is around 37, so double that, 74. So that's this idea of K-edge, and you're taking advantage of that by setting your energy level around twice that, so around 66 to 74s, where you want to hit that stuff when you've got a contrasted study to maximize your photoelectric effect and maximize which is better for contrast relative to Compton scatter. Alright, so just some vocabulary words here. You will read in books that there's a thing called linear attenuation, then you will sometimes read this thing called mass attenuation. Well, what does that mean? What's the difference? The difference is only relevant for the purpose of being tricked on multiple choice. That's the only reason I really introduced the concept of mass attenuation. So linear attenuation basically says that if you've got a gas and you've got a liquid and you've got a solid, and you could have the same amount of something, but it's going to space out more depending on um, the form that it's in. That it's going to take longer to go through the gas and less solid or liquid and then solid, so they're different. So linear attenuation looks at these three things and says they're different. Mass attenuation looks at these three things and says they're all the same. So that's the only, who cares otherwise, just don't get those confused. Now, linear attenuation, or you more commonly see it written as linear attenuation coefficient, is much more clinically relevant. And it's usually used in a relationship with half-value layer, which was something that we mentioned before, which is the thickness of a material needed to cut the power of that X-ray in half to half-value layer. So, and this is the typical relationship is when your linear attenuation coefficient goes up, your half-value layer goes down. So something like this. So if you have more energy, so you have more penetrating radiation, that is going to mean that your linear attenuation is going to decrease, and your half-value layer increases. So if you remember that the third half layer had more penetrating capacity than the second half layer, and more penetrating capacity than the first half layer. And then the opposite's true. So if you're encountering more dense tissue, more collisions, so this is like being filtered, the half-value layer is decreasing and your linear attenuation is increasing as it goes through more difficult penetrate, so more collisions are happening. So just remember that those are sort of opposites of each other, and then depending on how the question is written, you'll understand that relationship. So the next talk is a longer one. It's on general X-ray concepts and a whole bunch of miscellaneous topics that I haven't mentioned thus far with regard to X-rays, and then I'll follow that up on a mammo lecture, which will finish out the discussion on basic X-ray stuff, and we'll move on to more elaborate topics.